a fundamental theory that unifies or goes beyond our existing fundamental theories, that is general relativity and quantum theory. And in particular, I'm going to talk about the problems of quantum gravity and also how to address them with a very basic tool of a theoretical physicist, which is to build a model that helps you understand the problem. So that's why I've titled my talk as Spin Systems as Toy Models for Emergent Gravity, which is what I work on. So I am going to tell you things about quantum gravity and current research, but I also do really want to talk about just how do you do theoretical physics, how do you break a pretty complicated problem into something that maybe you can understand how to do. One more thing I wanted to say is that this work is also very interdisciplinary, as the general open architecture of this building is supposed to encourage. So these are some of the collaborators that I'm working with, and it's a mixture of people in quantum gravity and quantum information theory, condensed matter physics, and so on. And the talk, the first half is going to be general things about quantum gravity and what people do, and the second half is basically what I do. Okay, one more thing. Ask me questions during the talk. So if you don't understand something, it's probably because I'm not saying it clearly. So stop me and ask. Okay, so one generally says that quantum gravity is a theory that we do not yet have, we are looking for, and it should, in some sense, unify general relativity and quantum field theory, which are the current theories that we have that describe the universe at the most fundamental level. So why do you need something that goes beyond them or unifies them? So one thing is that, first of all, these two theories have been very well tested and are extremely successful, but they do ultimately fail, in the sense that, for example, in general relativity, the theory predicts black holes, but it doesn't tell you what the black hole really is. You get a singularity, meaning that the curvature of space-time blows up, goes to infinity. That when you get an infinity in your theory, that really means your theory has broken down. It's beyond its limit of applicability. Also, it's similar with the Big Bang. When you go backwards in the history of the universe, you get another singularity where the theory breaks down. Quantum field theory, you get a similar effect. So you get, in quantum field theory, you have effects like the photon can pair create into an electron and positron pair, which in turn can emit another photon, which can pair create, and so on. And so you got this infinite sequence, which we can control using renormalization. So we know how to deal with it. But the fact that ultimately the theory has infinities in it really tells you that we do not understand the fundamental physics. And one important thing that you might observe here is that the infinities have to do with probing the small structure of space-time. You actually are trying to squeeze this infinite process in a very small piece of space-time. Okay, so this is the type of problems that you get from each theory in itself. You get another set of problems if you try to actually combine the two. So, for example, as we heard earlier, in quantum field theory, you get vacuum pair creation. So you can get a particle and antiparticle instantaneously pop out into existence and then disappear. And this is something that you can test in the lab that actually does happen. So you get a Casimir effect, where you can see a force on two plates due to this pair creation, vacuum pair creation. So this is a real effect. But now, if you think, how does this combine with general relativity, you would have that there should be all this matter popping in and out of existence everywhere in space, and all of these little blobs curve space around it. And actually, if you do the calculation, there should be so much stuff getting created all the time that actually the whole of space-time should curve up. And you should be able to see an actual real effect, which you don't. So this is a cosmological constant problem. So if I actually put the two theories together, I get predictions that are definitely wrong. So how are you supposed to reconcile the two theories? So what I want to do first is take things slowly. So let's see what happens if you actually try to put general relativity and quantum theory together in the most straightforward, naive way. All right, so the first thing is that general relativity is a theory about space-time, Okay, so you probably know that. But it's very important that this space-time is a collection of physical events, meaning that something becomes your past because a physical event took place. So in particular, at the end of my talk, this talk will have happened to you for a physical reason, which is that if I'm sitting here and this is my screen and my person, then the waves from my voice reach your ears and the photons from the screen reach your eyes. And it is this physical process that creates your past. It's this physical process that makes you walk out of this room at the end of the talk and say that you just saw a talk. The talk was in your past. Now, that means that, of course, the physics of the universe can affect past and future. So in particular, if by some theoretical construction behind this screen there happened to be a little black hole, because being a theorist I can make these thought experiments, what would happen is the photons would instead go backwards, they would not reach you. So you would sit there in your chair, you would walk out after the talk, and the talk would not be in your past. So this is what we mean by saying that space-time is the result of the fact that causal structure is dynamical. It's a collection of all events that have occurred that creates a space-time. And this is really a collection of physical processes. All right. Now, I have to now take into account the fact that matter is quantum. So the matter that made up the black hole behind the screen should be treated in a quantum way so that I'm fully consistent. So the same way that in quantum theory you can have a situation of a superposition of an electron taking one path and another path, so you can have superpositions of electrons of the same electron in two different places, I should also now have superpositions of the black hole being behind the screen or somewhere else, right? So the correct physical description, according to this, is a description in which at the end of the talk, if you were going to take quantum effects properly into account, you should be in a situation where the talk has happened and not happened. So you should have a superposition of your pasts. And my question is, well, does this actually make sense? I'm not saying that the talk happened or didn't happen. I'm saying the talk happened and didn't happen. What can I possibly mean when I consider quantum superpositions of causal structures? Is that a sensible thing to do? First of all, we don't ever see that. Strictly speaking. And this is another thing to appreciate, is that talking about superpositions of spacetimes, which is what I'm talking about here, is actually one level worse than the Schrodinger's cat paradox. Because it's, okay, so Schrodinger's cat is a big problem, so I don't really know how to make sense of, or rather, well, we don't see superpositions of cats being dead or alive. But perhaps I can push the problem to the observer, and maybe it has something to do with the measurement and so on. But if I'm talking about the entire universe, I do not have an outside observer who is going to decide when they're going to make the measurement. So I really have to make sense of a quantum theory of the entire universe, which is a problem of quantum cosmology. And that is not trivial. I'm just going to basically say the same things here again in a slightly more technical way by just going to general relativity and the Einstein equations. So the Einstein equations, together with the geodesic principle, basically tell you that matter tells space-time how to curve, and space-time tells matter where to go. All right? This is supposed to be the central physical content of general relativity, which is what we were discussing before when we were saying that a space-time is a collection of physical events. So now there are two things to take from general relativity. One is what we said before, that the space-time metric, G mu nu, is not a background, is not a fixed stage, as they say, on which stuff happens. It is part of the equations, so the metric is dynamical. It can be affected by the tensor, the matter content of the universe, T mu nu. The other important thing is that the relevant physical quantity is not really the metric, but the metric modulo diffeomorphisms. So I could illustrate this way. This is a chunk of well, let's say this is space-time in 2 dimensions, and the blue line is space at one time. So I'm looking at a little piece of a space-time here. So what a diffeomorphism does is it's a smooth transformation that maps points of a manifold to points on a manifold. So it shifts around points. And the important thing is that if I were to look at the causal structure, so for example, this particular sequence of events where, I don't know, maybe, so I'm here, I'm telling you about quantum gravity, and I'm also telling your friend about quantum gravity, and then afterwards you're going to talk to your friend about the talk. So there is a certain causal sequence here. So those sequences can themselves get, they can be deformed by a diffeomorphism, but the actual causal order will not change. Okay, so that's the important thing. So the actual coordinates you might use to describe the points in a manifold are not the physically invariant quantities, it's the actual order of the events. So only events that their causal relations are physical. And the metric is dynamical, is basically the content of general relativity. And in this talk, and in several approaches to quantum gravity, this is taken as a principle that should be carried over to the quantum gravity theory as well. And so we are going to call this principle background independence, the principle that only events and their relations are physical. There is one more thing I want to say at this point, which is if you have pure gravity, so there's no matter in your universe, there is no good way to mark these events. So I just marked my events in the previous example by using you and me in my talk and the photons of my talk and so on. But if I don't have matter to mark the events, then a diffeomorphism can shuffle any point in a manifold to another point. So actually, time evolution itself becomes a symmetry. So it's almost as if nothing happens. And so the statement that time evolution is a diffeomorphism is often called the timelessness of general relativity. So if you quantize general relativity along the lines of what Francesca was talking about earlier, you will find that evolving the universe at a given time forward is actually a constraint. So in a sense, nothing happens. It's not really a true evolution. So instead of having a Schrödinger equation, you have an equation of this form where this is the wave function of the universe. So maybe these are the basis states for the wave function of the universe. And you evolve this forward with a certain operator that you extract by quantizing the Einstein equations. But the right-hand side, instead of having the d by dt of the Schrödinger equation, has a 0 because you have symmetry instead of time evolution. And I think it's fair to say that nobody really knows what that 0 means. I know how to understand the Schrödinger equation. I do not know how to understand the Wheeler-DeWitt equation, which is this object. And this is called the problem of time in quantum gravity, and one could have a whole talk on analyzing this particular equation, but that's not what I'm going to do. Now, since I'm describing new physics, it's very important to tell you at what scale do we expect this physics to happen. So the scale of quantum gravity is the Planck length, which is what you get by dimensional analysis if you combine the Newton's constant with the Planck constant and the speed of light, and you get the ridiculously small length of 10 to the minus 35 meters. Now, you say that at this scale, the quantum effects of the gravitational field become important. I actually prefer to think of the Planck scale as the scale at which you reach fundamental limits to space and time measurements. So if you want to measure something, say the distance between two atoms, you will want a microscope with probes that have a Compton length comparable to the resolution you want to obtain, right? So the higher resolution you want to obtain, the bigger the bigger the energy of your microscope should be. So the problem that arises at the Planck length is that the resolution that I would need to make Planck scale measurements is so small that the microscope itself will curve the space-time I'm trying to measure. So I cannot actually make measurements beyond the Planck scale. So we know for sure that we need new physics at the Planck scale. And we have these questions I was discussing before of, is the new physics a physics of quantum superpositions of space-time? I do not know. But it's important to say that even though the characteristic scale of quantum gravity is the Planck scale, that does not imply that quantum gravity effects are Planck scale effects. So this is quite a statement here. So to be precise, what I want to say, to point out, is that the need for new physics is not restricted to Planck scale. So first of all, one thing that often happens if you try to construct a new theory of space-time is that you break Lorentz invariance. And there are astrophysical constraints to breaking Lorentz invariance in certain ways at the Planck scale. So in fact, current astrophysical observations can, under certain circumstances, reach the Planck scale. But then another big place where quantum gravity may be relevant is all the physics that we do not know. So actually what we have right now is that 25% of the universe is dark matter, 70% of the universe is dark energy. We don't actually know what this new physics is. If you work in quantum gravity, you might have a decent hope that all of this unknown out there may have something to do with the theory that we're missing. There is also all sorts of other problems. For example, early universe is described by inflation, but we don't actually have a theory of what inflaton is, and so on. So there is plenty of physics out there. We only know 5% at best of the universe. And so maybe that's places for quantum gravity effects. All right. Now, of course, when you have all of these things that you might want to answer, you have many options on how to proceed. So you, depending on your long shopping list, you can have your favorite brew of constructing a new theory. And I'm not going to try now to survey all the different approaches that people have in quantum gravity because there's no point. So I'll pick some particular direction. And the one I'll pick is obviously the one I already set up in the introduction, which is to try to push the concept of background independence as far as we can go with it. So I want now to think of background independence beyond classical spacetimes, beyond general relativity. And I'm going to explore two versions of background independence and two different theories that you can construct to explore that. So in the first version, let's call it background independence 1, is a statement that there should be no preferred geometry in the formulation of the quantum theory of gravity. And quantum gravity is given by a quantum superposition of quantum geometries. So what I need to do to get to a quantum theory of gravity is replace the classical light constructor with some quantum superposition of light constructors or quantum fuzziness in the light constructor. Now, to summarize, how did we get to that? How do we get to the idea that there should be quantum spacetimes? We first said that a spacetime is really a collection of physical events. Then we said that physical events, well, matter really, is quantum. Quantum means that you have to take superpositions into account, and therefore you expect to have at the fundamental level superpositions of spacetimes. All right, good. So now how do you make this into a theory? You have to ask some specific question. For example, an important question that you may want to ask is to show that if you start from a quantum superposition of spacetimes, you have a way, a method, a theory that tells you why we don't live in a quantum superposition of spacetimes, but we live in a nice regular spacetime, our world. Why is our world the most likely configuration out of this quantum superposition of spacetimes? Now, this question stated this way is not very easy to attack. So I first need some tools. I need to make it into something that I can reduce, that I can work with quite easily. And so what I'm going to do is make a model of a spacetime so that then I can consider quantum superpositions of that. And it's important here to, not to explain, I'm sure you know, but just to stress the role of models in physics, right? So you make a very simple version of something that captures the precise physics you want to analyze, and then you push that as far as it goes so that you learn something. So the classic way to say that is that for a normal person, this is a cow, while for a physicist, a cow is a spherical object uniformly filled with milk. So the idea here is to do the same treatment to a space-time. And the usual way that instead of having a full-blown metric g nu nu, I have a model of it, is to consider curvature in terms of triangulations. So if I now have, let's do it in 2 dimensions, right? There's higher dimensions is just a more complicated version. So in 2 dimensions, I can describe curvature by gluing together equilateral triangles. So every angle of this triangle is 60 degrees. And depending on how I glue them together, I can describe curvature. So if I have 6 equilateral triangles around a point, then the curvature around this point is flat. If I have less than that, then I have a negative curvature. And if I have more than that, I have positive curvature. Straightforward? So this would be my triangulated cow. And this is useful because, for instance, I can make now a space-time version of it. And the only difference is that instead of just having equilateral triangles, I have equilateral triangles with sides that are time-like and space-like. And by gluing those together, I get a triangulated version of a space-time.
So those are equilateral?
Yes, they're equilateral. So I've drawn them this way because I'm squishing the equilateral triangles on a flat page. So you can just go around every point and count those and understand what the curvature is from those. And by putting these things together, I can get, for example, a universe. So in this is just 1 + 1 dimensions. So here, my universe, the space at a given time, is only characterized by length. There is not very much information other than length. So this is, for example, a universe of length 4, 1, 2, 3, 4. And it ends with a universe of length 4. And in the middle, it's a universe of length 5. And this is one particular way to extrapolate between those two. Excuse me? L. Oh, yeah. I think it's T, actually. It just doesn't show properly. It's T. Oh, I'm sorry. What was it? Did you refer to this? Yeah, this is T. So this is a particular sequence of such objects, right? With boundary conditions, closed boundary conditions. Okay, and now the good thing is that with triangulations, I've reduced the problem to combinatorics. So for example, if I were to tell you can you please tell me how many metrics can I put between this configuration of the universe at this time now and a configuration of the universe at a later time, I don't really know how to enumerate, how to take basically an integral over all the possible g mu nu's that I can fit between 2 particular instances of the universe. But if I reduce it to triangulations, I can basically ask you, if you start with a universe of length, say, 5, and you end up with a universe of length 100, how many spacetimes that are made from, say, 1,000 triangles can fit between those? And this can be a complicated counting problem in higher dimensions, but it's basically a straightforward problem. So in that sense, this is a nice model. And now there is this particular work that is based on these triangulations due to Ambjorn and Lal and collaborators. And I have to point out, this is some of the nicest stuff in quantum gravity, and Renate Lal is a woman. I didn't pick that work because we are all women here. It is actually one of the best results in quantum gravity. So the way that you do this now is that you have a quantum theory where you get an amplitude to go from the universe at a certain size to a universe of some other given size that is the sum of all triangulations that you can put between those two. And what they did is that they explored a particular property of spacetimes, of triangulated spacetimes, which they call a causality condition. But what it really means is that you advance everyone at every step. Yes. Yes. Well, you can then sum over all possible number of triangles that you could have summed over. But actually, for the purpose of the calculation one needs to do, it's enough to sum over. So you basically calculate certain expressions that are functions of the number of triangles, and then you take the limit where the number of triangles becomes some very large number or goes to infinity, and you want to see if that converges. So it's sufficient to just do the calculation for a given number of triangles. Right, so what I was saying is that you want to advance everyone at every step, which is the type of configuration I've showed you here, where this is time 1 and this is time 2, and at one click of the clock, I have moved everybody forward. So to illustrate this better, I can have the standard image. Actually, this is really the world that we live in, the way that we understand it, where this is a given instant of time, that's the next one, and that's the next one, and at each instant of time, everybody has changed, right? And so in terms of a triangulation, this is the type of configurations I had before. However, this is really the Newtonian world that we are familiar with. This is not quite how it works in general relativity. In general relativity, you have local evolution. You don't have a global clock. So, in fact, if these different colors are slices of space at given time, you can evolve each one locally. So you can have bubbles, multi-finger time evolution. And so in terms of triangulations, the general relativity type of evolution would, for example, allow triangulations like this, where this is the universe at a given time, this is the universe at a later time, and then this is a later one, and then you keep going like this, and so on. And now, what it turns out, and that's what these guys found out, is that it makes a difference which triangulations you count. And if you use just those, the ones where everybody advances at the same time, then you get very nice results. You get that the most likely space-time has a good dimension. So you get a dimension for space, which is basically 3. So I should say that this is a Hausdorff dimension, which is what is most natural in this type of models. And the Hausdorff dimension is you sit in the triangulation and you go out a certain number of steps. And what you do is that you look at how the volume how the volume changes with the radius that you go out. And that, the ratio of volume with radius, the radius to the power of the dimension gives you the volume. So when you can look at how volume changes with radius as you go out from your given point, you can calculate a certain dimension, which is called the Hausdorff dimension. So you do this work, and you find out that with this condition, you get that the most likely spacetimes are 3 + 1 dimensional, which happens to be our world, and that they're smoothly varying, meaning that you have configurations like this, where the volume of space now is comparable to the volume of space a little later, so you don't get huge jumps in the size of the universe. While if I use the more general notion of time, then I get very bad results that had been known for a long time before that. So the average, the effective dimension is either infinite or 2, even if my building blocks are 3-dimensional. So you get bad answers. But that is a little bit, I mean, in a certain sense, it's really very nice that you can start with this very simple construction to describe a space-time and get smooth varying geometries of the correct dimension come out. But the problem is that this is more like Newtonian time, while this is more like relativistic time. So what's going on here? We are indeed the most likely configuration, but if you use a notion of time which perhaps disagrees with general relativity. So this answers some questions and raises new questions. Also, the type of questions that you can answer with this kind of model is a bit limited. So when you say, are we most likely? Yes, we are, if all that you're asking is, what dimension do we live in, and do you get a smoothly varying geometry? This still does not answer my question of what does it mean to have a quantum superpositions of pasts. So for that, I need more than smooth geometry and the correct dimension. So in essence, what I need is to show that apples fall in these quantum spacetimes and understand, do I get a superposition of an apple falling and not falling? So the rest of the talk is going to try to make a model where perhaps we can try to address that question. But I'll go back to the very beginning and start all over again. All right? I'm just going to ask a whole new set of questions and construct new models for those questions. So I'm going to go back to this picture of the quantum superposition of pasts and say, well, you know, okay, what I did here is really put together quantum theory and general relativity, but maybe there's something fishy. Maybe this is really wrong. So instead of the previous version of background independence where I said that there should be no preferred geometry in the spacetime, I will now try a stronger version of background independence, which says that there are no geometric or gravitational degrees of freedom at all in the fundamental theory. That geometry and gravity is not fundamental. It is in some sense emergent from something that doesn't have those properties. Now, when you say emergent, what you generally mean is that the behavior of the system has no explanation in terms of the constituent particles, but instead is a result of their collective behavior and interactions. So when you look at this picture, you may be looking at a river or you're looking at the molecules of the river. So in a certain sense, the speed at which the river flows is not fundamental. It is an emergent property of the collective behavior of the molecules that make up the river. When you talk about a wave, the description of a wave is an emergent object, is an emergent concept. At the fundamental level, there are no waves. It's just the intermolecular potential of the molecules that make up the river. So we want to pull the same thing in gravity and say that gravity and the actual notion of space-time itself is more like the river is to the molecules. Now, we want to do a model for that. And to start, we'll just go back to the paradigm of emergence. So emergence is really the topic that's studied in statistical physics. And the classic paradigm is the Ising model. In the Ising model, what I have is a lattice with spins. And depending on how the spins are aligned, I am magnetized or not. So if all the spins are aligned in the same direction, then I say I'm magnetized. If the spins are randomly aligned, I'm not magnetized. And so what we want to do is construct a theory where instead of the magnet, we have here space and gravity. And the question is, what should go there? Right? What underlies space and gravity? So what is the Ising model analog for gravity? So first of all, you have to say what you mean by emergent space. And that is not very easy because physics, you do always assume space. So you have to find a way to talk about space itself, starting with something that obviously doesn't have that notion. Otherwise, you would be circular. That's not very easy, so I'll tell you what our attempt at it has been. So first of all, what we want to understand is what characterizes, if you like, space. Why do we think that space is a useful notion? So the first thing, of course, is locality. So we have an idea that we're in this galaxy, and then there's some other galaxy somewhere else, and it takes us a while to go from the one to the other, right? Which is what you mean by locality. So the distinction between here and there is something very essential to space. If you had an object that didn't have a distinction between here and there, that would definitely not qualify as space. So this already leads you to a very simple notion of locality, or adjacency, if you like, which is networks. So the most basic way that you can describe adjacency is generally a network. So in a network, you have the notion of this node is close to that node because they're only one step away, while this node and that node are further away because you need to take 2 steps to go from one to the other, right? It's really simple. So a network basically always encodes adjacency. That is a notion of here and there. So we will use networks to describe locality and adjacency. The other important characteristic we think of space is, of course, its symmetries. So ultimately, like with other things in physics, it's symmetries that make a certain notion useful, and it's not different with space. So the physics of playing tennis is the same everywhere, meaning that you have translation invariance, and then there's other symmetries that characterize, say, a Friedmann-Robinson-Walker universe. And it is the existence of those symmetries that makes space a useful notion. So, for example, if you lived in a universe, which is allowed in general relativity, in a metric where you have huge variations in curvature from one region to the next region, and it's just some completely crazy geometry with no symmetries whatsoever, it would not have occurred to you to use that object to base your physics on. So it's the fact that we live in a very regular world with translation, rotation invariance, Lorentz symmetries, and so on, that made Minkowski spacetime a useful object to use. And it's why we base all our physics on space. So in that sense, if I'm going to think of adjacency in terms of a network, then to have regular space, I need to have a particular order in the network. For example, if I have a cubic lattice, that would be a good candidate for 3-dimensional flat space, say. All right? That is all pretty straightforward, right? So now, however, I want a model in which space emerges from something that you would call no space. And this amounts to, if you like, an alternative scenario to cosmology. So currently, standard Big Bang cosmology, you assume a Friedmann-Robinson-Walker geometry all the way to the Big Bang, which is actually a little bit fun if you think about it. We live in a flat space, and if you go back to the history of the universe, it's flat, 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 and then there's the Big Bang. Another possibility would be that geometry is not really fundamental. So as you went back, when energies became high enough, then the whole notion of space-time geometry might break down. So we would like to describe a simple model of a universe that started from a non-geometric phase and ended up with a geometric phase. And as I described it before, the way that we are going to distinguish between the two is really by characterizing the geometric phase we live in as a phase in which you have locality, you have 3+1 dimensions, you have translations and certain symmetries and so on. And the non-geometric phase, none of those existed. And I'm going to still base my theory on networks. And therefore, what I really want to be describing is a situation where I go from a highly regular network, which is which is presumably very connected so that there's no notion of locality, to a very regular network. And you can think of this process as a process of going from a very hot configuration to the cold, ordered world that we live in. So you can think of geometry as the frozen phase that we ended up in. And what I'm looking for is a way to cool the universe from here to there, which really will mean writing down a Hamiltonian that transitions from here to there. So let me make this a little bit more precise. So the basic idea is to write my networks as spin systems, in fact, quantum spin systems, in which the links are quantum degrees of freedom. So the way I can think of it is this. If I have, for example, these two nodes here are connected, right? So I have a link between those two. So I want to think of that link existing as being in the one configuration, being in the one state. While between these two nodes, this one and that one, there is no link. So instead of saying there is no link, I will say there is a link, but that link is in the 0 state. So what I'm going to do is promote every possible link between two nodes to a quantum degree of freedom that can take values 1 or 0. And you can think of those as qubits of adjacency. So if you had a universe of n constituents, there are n choose 2 possible links. So this is a universe of 4 things, and these are all the possible links between those 4 things. And what I'm saying now is that you can model this by thinking of every link as having 2 possible states, 1 or 0. 1 means I'm connected, 0 means I'm not connected, and I could be in a superposition of the 2. And so the state space of such a model, it's really a model of quantum adjacency, would be the tensor product of a state space for each link, and each link has basis states 1 and 0. Yeah? So the generic configuration, a state here, is going to be superposition of subgraphs of the complete graph on the n constituents of the universe. Yes? If you have a complete graph, you have permutation symmetry, presumably.
Right. So isn't that then, so they're not independent. So you lose locality, but you have a lot of symmetry. I mean, these two concepts are not independent in that example.
So your question is,
You wanted to say this complete graph is where you have no geometry, however, it has a lot of symmetry. So it has no locality.
yeah, okay. So I guess what I'm doing is this. So let me just say again what you said, right? So what I want to say is that I'm going to go from a world where everybody's connected to everybody else. So I'm filling in a little bit the gaps here. Where basically everybody is on the one state. And I'm going to think of this as the no space configuration. So I will say that here there's no notion of locality because everybody is really connected to everybody else. So you cannot really split this guy into subsystem in any nice way. And I want to transition from this to something with a different symmetry. So actually both of these networks, this one and this one, they both have 10 nodes. The difference is in the links. Right? So this is this really is the same as this graph with a lot of zeros in the appropriate places. So this link is 0 and so on. And then this graph has translation symmetry. It has locality in the sense that it takes a while to go from here to there and so on. So your question is, here there's no locality, but there's permutation symmetry. There is translation symmetry, and there's locality. So I guess the idea here is that, like you would do when you cool something, is that you break the symmetry to a much smaller symmetry. And locality seems to be the outcome of that symmetry breaking. Do I have more questions now? Do I go on? Okay. So now how do you do the transition? You have to write down a Hamiltonian that performs the cooling of the system. So I'm not going to go into the details of the Hamiltonian, but basically there's a couple of parameters in it that control the final configuration. So you can start from the completely connected guy, and there's a parameter here that tells you that you will get minimum energy if the degree of all the nodes, the number of links that come out from a node, is equal to this parameter V naught. So for example, if I choose V naught to be 3, all of those graphs minimize this term in the Hamiltonian. Now, from those graphs, if I wanted, for example, to be freezing my universe to a 2-dimensional flat space, this is not good because this is in effect 1-dimensional. This is not good because it's not flat. This is good. Now, the difference between those three is the distribution of links around vertices. And I control that link distribution with another term in the Hamiltonian. which again has a parameter here, which if I adjust the right way, I can end up with this graph here, which I hope is not too fuzzy, and you can see. It's honeycomb lattice with periodic boundary conditions. So it's flat space in 2 dimensions. And this configuration here is the minimum of those terms in the Hamiltonian. So I can start with a configuration of the universe which is, in my simple model-like brain, the world with no space. So if you lived in this universe, you would never think of using locality or space or Minkowski space as a good way to describe the world, and end up with flat 2-dimensional space. Now, I can pull another trick using the work of some other people, which is really cool, and say that instead of when I'm connected just being connected, I could be connected in different ways. So instead of a link being on being in the one configuration, it could be in different colors. And with the right massaging of the Hamiltonian, putting the right terms in the Hamiltonian, this type of model gives rise to emergent QED. So the way that you can think of it is that from this configuration, I could actually lower the energy even further if I have closed loops of alternating colors or open strings of alternating colors. So this guy here has even lower energy than that. And the closed loops of alternating colors correspond to fluxes of photons through those loops. And the ends of the strings of alternating colors behave like electrons living at the ends of those strings. And so this is a theory of emergent QED due to some other people that you can adapt so that your universe starts here, and then you get emergent space in the sense I just described, and on that you also get emergent matter. So this is a simple model where you get matter when space emerges, the way I just described. Yes? So you can think of them as, so actually the way that you do that is when I had just 1 and zeros, you could think of them as a 2-dimensional qubit space, right? And I can have a degree of freedom representing that. So now I can add a second degree of freedom that says that when I am at 1, then the second degree of freedom, for example, could be +1, -1, and 0, as you do with angular momentum. And when the link is 0, then there's no color either. So you could have now 2 degrees of freedom, J and M, if you like, so where the J is 1 and 0, and the M is a different colors. And in the limit where the M degrees of freedom become a rotor, a continuum, so you can have an infinite number of levels, if you like, an infinite number of colors, then you map this term, the Hamiltonian, to QED. What do they represent fundamentally, if that is the question? Is not so clear. So, for example, the way that Wen and collaborators talk about that is, do photons and electrons have to be fundamental, or could they be emergent? Why do we think of elementary particles as being fundamental? Could they be emergent as the order of something else? And the something else here is those spins, these colors on the spins. I'm not so sure how you're supposed to think of those. So the loops are important because in this Hamiltonian, if you look at the details of this Hamiltonian, when you have a loop of alternating colors, you have less energy than when you have a black loop. But this is the way the Hamiltonian is designed. I can tell you some more about that afterwards. I'm kind of hesitating here because unless I tell you some more about how it works, it's a little hard to say. Yes? Yeah? Right. So with those, with this state space that I gave you here and with this Hamiltonian, you don't get the other bosons. You get just QED. In principle, you could use the same, and there are similar tricks. A couple of different people have such tricks. You could also get QCD or other emergent theories like that, but this one I'm describing here doesn't try to do more than that. Yes, so in principle, it's a question of finding the right parameters to control what graph you want. I'm not saying it's easy to find the right one, but there is no fundamental obstruction to getting what graph you want as the lowest energy state. Okay, so I want to tell you something else you can do with that. So here what I have is a spin system with a local Hamiltonian, and from that I can actually get a speed of light from the local Hamiltonian. So I can do this in the following way. I can say, as you will probably believe, that if I have a local Hamiltonian, meaning that I have to talk to you before, and then you talk to her, and then she talks to Francesca, and so on, and we go around here, there's going to be a finite speed that information propagates, because we have to each talk to our neighbor before the information goes from me to the other end of the room. So the question is, what is the relationship between the speed of information propagation and the speed of light? And it turns out that in the model that I was describing to you before, they're actually the same, which amounts to really deriving the speed of light from the fundamental Hamiltonian in the spin system. And I can do that using the concept of the Lieb-Robinson speed of information propagation, which is a notion in quantum information theory. And this tells you that if you have a spin system, you could quantify the speed with which information propagates between this point P and a point Q by looking at the norm of the commutator of operators at these different points at different times, which would tell you something about the strength of the signal between P and Q. So these other people have estimated that the strength of the signal is bounded by some expression where these are the couplings in your Hamiltonian, and this is the number of paths in your lattice that go between P and Q. So if I give you a spin system with its Hamiltonian, you can actually calculate how strong is the signal between 2 points in that Hamiltonian. You can also rewrite the same expression in a way that defines a light cone, where this is the speed with which information propagates. So I can now go back to my model and calculate the speed in terms of the fundamental couplings in the Hamiltonian, which is some expression here. And it turns out that this speed of information propagation agrees with the speed of light in the effective Maxwell equations in the emergent matter I was just describing to you. And the reason that this is very interesting is because what do you have here? You have a spin system with a Hamiltonian, meaning non-relativistic quantum mechanics. So in principle, there is, as is the case with non-relativistic quantum mechanics, there is always a signal between me and wherever far away you want. This is Newtonian physics. This is a standard Schrödinger equation. But in effect, it looks like you have finite light cone structure in the sense that within the light cone, rather outside the light cone defined by this speed of information propagation, the signal does exist, but it's exponentially suppressed. So if I ignore the exponential suppression outside this finite light cone, then I have non-relativistic quantum mechanics at the fundamental level, but if I'm an observer inside the system, it looks like I have Minkowski space. I have a finite light cone structure. And it is very pretty that in the limit in which the discreteness of the lattice spacing goes away, so if I take the continuum limit, then the exponential signal of quantum mechanics outside the light cone actually goes to 0. So I get an exact Minkowski space from non-relativistic quantum mechanics through this route, which is nice. And another nice feature that I'm going to use in a second is that the speed that information propagates is not surprisingly proportional to the degree of the vertices. This is because I told you that the strength of the signal depends on the number of paths that connect P and Q. So the higher the connectivity, the more paths there would be between P and Q. So the speed that information propagates will be a function of the degree of the vertices. So I'm going to use that in a little while. All right. So one thing I want to point out here is that this type of models is an illustration of, if you like, a quantum gravity effect that is by no means a Planck scale effect. So an obvious way to look at that is by considering the type of system I described versus the horizon problem in cosmology. The horizon problem in cosmology is the fact that if you look at the sky, everything is at the same temperature, even when it's at opposite parts of the sky. I will actually, maybe it's actually easier to say what the problem is if I give you an 1+1 discrete version of it. So this is a sequence of the universe at different times. And let's say this is the Big Bang, and this is us now. So you have the backward light cone from where we stand. And then you can draw the forward light cone from the Big Bang, for example, from this point here. And you can estimate how long it's been since the beginning of the universe. And you have a problem. The problem is that, for example, this point and that point have not been in causal contact in the beginning. So why are they at the same temperature? That is the horizon problem. What could be a causal mechanism for those guys to be at the same temperature? So the way the problem is normally solved in inflation is by introducing a period of exponential expansion in the beginning. So even though this time interval was very short, the universe was expanding very fast, so these light cones were really much wider than I've drawn here, and that brings those points in causal contact. In the scenario we're describing here, what happens at the beginning is that really everybody's connected to everybody else, which gives you a different type of causal mechanism for that. Now, the point I want to make from this is that this model illustrates the effect of a transition in the causal structure, which is, in principle, an observable effect. It has nothing to do with the Planck scale. In fact, the problem with this type of theories is not how to probe the Planck scale, is how to avoid throwing out your theory, because it contradicts observations. So it's interesting to try to play around with quantum gravity theories in which you can be ruled out. You might have observable effects that get ruled out. All right, so I wanted to show you a somewhat different model based on the same kind of game, which has a different purpose. So in this model, my purpose is to go back to gravity now, and to this concept that we were discussing before, that according to general relativity, gravity can be understood as geometry tells matter where to go, and matter tells geometry how to curve. Now, this type of behavior in principle is really simple. So I could imagine modeling it in my simple network spin systems. And my question is, if I had a spin system that behaves like that, does the arrow go the other way? If I have a spin system where I realize this type of behavior, do I automatically have gravity? If yes, that's great. If no, why not? So I will make now a variation of the system I had before so that I can start making it behave like this. So my system is going to be again networks, and I will again forget about the colors now, right? So every link now can be 1 or 0, so connected or not connected. So the black link here is 1, this link is 0. But now I can also have particles, bosons, on the vertices. So there can be a particle on a vertex or not. So the state space of my system now is a tensor product of all the link state spaces, which can be 1 or 0, or the vertex state spaces on which bosons can live. And I'm going to have an interaction between matter and geometry. So I'll be able to exchange geometry and matter, which is done with this term in the Hamiltonian. And what it does is the following. I can go to this graph here, and I can erase this link. And where the link was, I put two particles at the vertices of the original link. This is a unitary process, so I'm turning the energy of the original link into two bosons. So if you like, I take away some space and I pair create two bosons. It's a unitary, so it can also go the other way. I can find two bosons, and I can erase the two bosons and create a link where they used to be. And then I have a hopping term in the Hamiltonian, and according to that hopping term, the bosons can move around the graph. But it's not an ordinary hopping term, in that there's a projector here that tells you that you can only hop where a link exists. So this particle can hop to that vertex in one step, or to that vertex, but not here, unless it takes two steps. And this is very nice, because the way to understand this is that it is the behavior of the matter that gives the graph the meaning of space, in the sense that the graph tells you where the matter is allowed to go. So you understand space from how the matter behaves. Yes? You can put fermions, yeah. So this is a very simple model. So does it do anything at all? Thank you. Well, in the beginning we thought that it's too simple to do anything, but it turns out that it's actually quite a bit of fun to try to do things with it. So the obvious thing to try is, can you make a toy black hole? And if you can, does it attract anything? And it turns out that you can. And of course, the obvious candidate for a black hole is a region where you're very highly connected, because you would have very high energy density in that region. And now you can imagine being a boson jumping around this network, and think of what would happen if you get to this point. What would happen is that you have many more ways to go inside than outside, because there are many more links inside. And once you're inside, you'll just start going around the inside. So in that sense, this will act as a trap. And you can make this more precise by looking at this speed of light that I was telling you before about, and the fact that it is proportional to the degree of the vertices. So the speed of light outside will be proportional to 4, because that's the degree outside, while the speed of light inside will be proportional to the size of the guy inside, because for a complete graph, the degree of the vertices is basically the number of vertices. And so you can now do an analog of optics, and you can calculate the critical angle for total internal reflection using Snell's law. And it's going to be a ratio of the two speeds of light. And so it tells you that the probability of light escaping is inversely proportional to the size of your toy black hole. So if the big region is big enough, you're stuck. And there is all sorts of other interesting properties that this guy has that remind you of black hole physics. And so I should also say that one can make all of this very precise. And in fact, what you can find is that particles that obey this Hamiltonian see an effective curved geometry, which in this case is a Schwarzschild geometry. And you could even consider doing an experimental analog of this object, would be an analog gravity system in the lab. Can I take 2 more minutes to just give the... Yes. Okay. All right. All right, so these are the models I wanted to show you. And so basically what I've done for the purposes of this talk, really, is take a principle from our existing theory, background independence in general relativity, and try to push it as a guiding principle, although it's not really clear how to use it. And we follow 2 possible paths. One in which background independence translates into there should be no preferred geometry. So what you want is quantum gravity given by a quantum superposition of quantum geometries. And the question is, how is it that we do not live in one of those? How is it that we don't see quantum superposition of geometries and we see classic regular geometry? And so this is one direction of work in progress. There is obviously no answer at this point. Otherwise, I would be telling you what the quantum theory of gravity is, So this is one direction of research. Another version to interpret the same principle is that there are no geometric or gravitational degrees of freedom in the fundamental theory, that you won't have quantum geometry, that geometry will be a classical emergent concept. And this is the second type of models I was describing. And you can try to break the path to quantum gravity into several steps. So in the type of theory I was describing, is basically a way to unify, if you like, quantum and gravity by saying that I'm going to start with quantum and I'm going to get gravity as something emergent. So I'll make them consistent that way. So what we try to do is replace the notion of spatial geometry with the notion of adjacency in the network. So instead of a metric, we had the concept of are things neighbors or not, which is what the network encodes. And then we said that a particular geometry, for example, a 3D Euclidean geometry, is a particular order of adjacencies that exhibit certain symmetries. And in that sense, our geometric world is a phase, is a particular type of configuration of the adjacency network. And then by promoting the adjacency to a qubit, having this superposition of 1 and 2s, we had a way to consider every network as a subgraph of the complete graph. And so that was a convenient way to deal with quantum geometries. And since these are dynamical degrees of freedom, the 1s and 0s were dynamical degrees of freedom, in that sense, we are already implementing an important ingredient of GR, which is that the analog of the metric is dynamical, just like G mu is a dynamical field in general relativity. The local interactions of our system mean that we get a finite speed of information propagation, and so we can define a spacetime with a finite light cone structure. It is an open question whether different kinds of emergent matter will see the same light cone structures. In general, they will not, and that is a difficult problem with this type of approaches. I'm going to go into this. And now you can try to be ambitious. So if I could really find a Hamiltonian that implements what I said, if I could find a Hamiltonian that behaves like matter tells geometry how to curve and geometry tells matter where to go, do I have general relativity? So I mean, my Hamiltonian could do a little bit, but I could imagine playing around with this and finding better Hamiltonians and better systems that do that. Do I have reconciled quantum with gravity? So one attitude you could take is if you have a system that behaves like gravity at a certain level, then you have gravity. If it, the classic one is if it looks like a duck and walks like a duck and talks like a duck, then let's call it a duck. So this would be the version where what you try to do to get to a quantum theory of gravity, you basically try to simulate the behavior of gravity in a quantum spin system, which would be a way to reconcile quantum and gravity. Okay, maybe it doesn't work. If it doesn't work, hopefully you, again, learn something. If it did work, you'll be, it'll be great. If it didn't work, you'll learn something. I particularly like it because in this approach, you really try to make something behave like gravity. So you try to explain the Einstein equations. You don't just quantize the Einstein equations. And I particularly like it because I have to admit that I never really understood general relativity very well. So it's really fun to try to make it come out of a system that doesn't start with manifolds, metrics, diffeomorphism, and so on, because you really have to understand, so what is it that really is general relativity? What behavior is characteristic of gravity? And the answer is not obvious, so these systems are a very nice way to understand that. I must admit that I would be quite happy if this version also worked. So get just some aspects of gravity in a system that is also non-trivial. All right, so I basically started with the statement that we only know 5% at best of what's out there. So I'm hoping that quantum gravity is some useful theory that describes physics beyond the Planck scale. So I would really like to look at approaches to quantum gravity that could, in principle, be ruled out, like Diana was describing, without having to probe the Planck scale as such. So I don't really think that it's likely that you can get the other 95% without changing something major in your understanding of the world. And my bet here is that just space doesn't exist. I described a way to try to describe world without space using models. Of course, you know, the obvious caution is you must not raise more problems than you solve. And the good news is that there is lots of observations out there that generally will kill your theory, but hopefully will help you shape it as well. All right, thank you.
Great, so more questions. Shall we have people line up? Do you want to have people line up again on each side, or do you want to?
Depends how much time we want to. Okay, so I'll check the bus and get some questions.
Okay. Okay. Well, I'll start at the person closest.
So what are some of the observational data that will be most useful in this respect?
So with this type of systems, and that's not special just to those models, the most obvious thing is that Lorentz invariance is not exactly preserved. So Lorentz invariance is presumably an emergent symmetry, and there are pretty strict constraints to Lorentz invariance. So it depends on how you break Lorentz invariance. You could rule your theory out or not, so that is the obvious place to look.
Is there anything observationally with regards to dark energy or dark matter that will be helpful here?
Initially, we tried to play around with that, and there were some ideas. I don't think at that level I can really say something about that. You know, one hopes that you have something to say, but it needs a little bit more building up before one gets there.
Okay, so unfortunately I'm not at all familiar with this theme, so I might have misunderstood things, but basically I got the feeling that the notion of time in general relativity and quantum physics is different. Yes. And you try to resolve this by getting rid of geometry.
Yes.
And would it make any sense to try to get rid of time?
Yeah, okay, that's a very good question. So I find it very difficult to get rid of time. People try. And there are other approaches, in a sense, complementary to what I was describing, where one tries to get rid of time. I find it difficult to get rid of time and compared observations, really. And so the attempt here is to keep time and get rid of space and concentrate the problems there.
There are people looking
try to get rid of time, absolutely, yes.
One simple question first. So at some point you said you showed an error or an uncertainty to the dimension. It was 3.1 plus minus 0.15, I suppose.
Yeah.
Where does that uncertainty come from?
I don't think this is not considered to be really fundamental because those results are numerical results. This here. And the error is within the error bounds. So you expect to have some such uncertainty. So that's not really worrying.
Okay, thank you. And also, how would you incorporate dark matter? Since this only involves interaction through gravity, do you think it would be...
Well, I mean, there is all sorts of things that you could do. I'm kind of hesitating to talk about things that are wildly speculative at this point, and my problem is that there's just too much freedom in the model. And so it does not make good predictions when you have too much freedom. But for instance, so you have connections in your network. So then, if you like here, there's a network underlying space, right? Mm-hmm. So one thing that is very likely to happen is let me just go here, is you transition from here to there, but presumably it's not going to be an exact transition, so there will be some leftover links. For example, there might be a non-local connection between here and there, left over from the high energy configuration. So the question is, what would be the physics of the leftover non-local connections? And if you cook it the right way, they can behave like whatever you want, really. So there is more physics to these models, but so I mean that's also what I was saying before. The models are really too simple and not strongly constrained enough so that I could make a decent prediction there. But you would like to get ideally. I mean, obviously, I can construct whatever Hamiltonian I want. So the value of this would be if I can combine different observations in one elegant way, rather than I can always come up with a Hamiltonian that does what you want if you only have one observation to look at.
So how many years do you think this would take until we...
Depends on the number of graduate students you give me.
Okay, great, thank you.
In the first interpretation that you did of the background independence, you were talking about our spacetime being the most likely one.
Mm-hmm.
Why does our spacetime have to be the most likely one? Why can't there be, like, there's the parallel universe theory where we may not be the most likely?
I just hate that stuff. Yeah, okay, so you could argue that there's all these different worlds and we happen to live in this one, and then you use the anthropic principle to say that we are in the world we're in because if we were in another one, we wouldn't be there. And I just don't see that this has very much predictive power. You would really like to predict something. So explaining why our world is the way it is something that a theory might want to achieve. You can give up on that, but I don't really see why you should give up on that. But yeah, people do. Faced with, I mean, this is a difficult problem. So but I just think the other is not a lot of fun to contemplate not answering that question.
Okay, thank you.
In your black hole calculation, did you try creating boson inside the black hole and see the edge erasure, how it affect the outcome of the calculation?
If the...
So when you create pair bosons, you kind of erase an edge, and
Yes.
then it decreased the degree inside.
That's right.
Did you take that into account in your calculation?
Yeah. So in fact, eventually the black hole will evaporate. So if you wait long enough, the density of links inside will be the same as the density of links outside. So the black hole will evaporate, and what you'll end up is the matter that has escaped is entangled with the links that are left.
Okay, great. Let's thank Fotini again.
Thank you.